All right, today we are going to be going over a section of the 100-page machine learning book by Andriy Burkov. Now, if you don't have this book, that's all right. If you go to themlbook.com, Andriy Burkov has made this whole book free with a read first, buy later principle where you can download the book, go through the chapters, go through the exercises, and then later if you decide to purchase it, you can do just that. Today what we're going to do is go through a specific chapter. That is chapter 9 on unsupervised learning. And specifically, we're going to be going over the new method which Andriy Burkov coined for finding an optimal K for K-means clustering. Now, if we go to this Notion page here, which is down in the description, you'll see a summary of the exercises, a summary of this chapter, an overview of the chapter, some notation, as well as some questions and some further reading down at the bottom. And you can duplicate this to your own Notion so you can go through these exercises yourself. We're going to go through chapter by chapter, go through some of these techniques that he's going over, and provide some additional conceptual questions as well as some follow-up exercises. So without further ado, let's go to the Google Colab notebook. In this example here, we're going to be comparing two methods of determining K, the clustering parameter in K-means clustering. We're going to be using the elbow method versus the prediction strength method that he outlines. Now, if you're not familiar with the elbow method, please go through the chapter and review this method as a way of determining the K or the hyperparameter for K-means clustering. Now, what we're going to do for this example in particular, we're going to generate a fake data set with the make blobs function in sklearn. Now, this data set is going to have a random number of centers between 2 and 7, and it's going to have a random standard deviation so that there's varying levels of overlap between these centers. And we're going to use the elbow method to try and determine the number of centers in this data set, as well as the prediction strength method. So the first thing that we're going to do is import the libraries. We're going to be using the random library in order to generate a number between 2 and 7, as well as generate a standard deviation for the clusters. We're going to be using pandas to store the data in a data frame, NumPy for some vectorized operations. We're going to be using matplotlib to generate these plots. We're going to be using sklearn cluster. We're going to import the K-means algorithm. From the data sets, we're going to import make blobs, and we're going to import train test split. Now, if you're not familiar of why we're using train test split with this unsupervised algorithm, please review the chapter. And the main reason is that Burkov suggests that we should approach this problem similar to how we would approach a supervised algorithm, in that we are going to split it into a training set where we're going to train our model, and then a testing set where we're going to test our model and then generate this prediction strength method. We're also going to use or import pairwise distances. This is a function that we need when we generate that helper function for prediction strength. So let's import these libraries. Now next, we're going to generate a random number between 2 and 7, and this random number between 2 and 7 is going to represent our centers, or the number of clusters that's going to exist within our data set. So I have n centers, random.randint between 2 and 7. Now this right here is just giving us a standard deviation between 3 and 4, and then rounding it to 2 decimal places. So let's import this. Well, let's run this. Next, we're going to generate the fake data using make blobs. So we have the features and the clusters. In the make blobs function, we're going to have 1,200 samples, 30 features, n centers is going to be equal to n centers. Cluster standard deviation is going to be equal to cluster standard deviation, and we're going to shuffle it equal to true so they're not sorted by cluster. Next, we're going to get our columns, and we're going to map them via string. So we have 30 features, so all the column names are just going to be a string representation of that number of what feature that is. We're going to store this data in a pandas data frame, and then we're going to look at the head. And so if we see here, we have our samples here, it's going to be 1,200, and we have our features. We have 30 features in this data set. Next, we're going to be going over the elbow method. So let's open this up. Now, first it says to fit the K-means model to the data set for all possible Ks. In this case, K will be 2 through 7. So we already know it's going to be 2 through 7. So the first thing we're going to do is store the range of possible clusters in a variable. So we're going to be going a little bit over 7. Let's just assume that we don't know it's going to be 2 through 7. Usually that's going to be around the amount we're going to store. So let's just do 2 through 11, just so we can get an idea of what it looks like when it's outside of that optimal range. Next, we're going to store our metric or within cluster sum of squares in a list so that we can generate our elbow plot. And next, we're going to start and go into a for loop. We're going to iterate for each k based on our number of clusters, ranging from 2 to 10. So k will first be 2, then 3, then 4. For each k, we're going to train a model, and we're going to append that within clusters sum of squares to our WSS list. Great. Now that we have our for loop set up, we're going to iterate for each k, and we're going to subsequently append our within cluster sum of squares to our list. Perfect. Next, we're going to generate our elbow plot. Now we have our k's and we have our error metric or our WSS, so we just have to have the number of k's on the x-axis and our WSS on the y-axis. All right, we have our elbow plot here. On the x-axis, we have our k's, and on the y-axis, we have our within cluster sum of squares. So let's add some labels to this just so it looks a little bit nicer. Now, by the looks of this, we see this inflection point, or the elbow, is at 4, so that's likely our number of clusters. So let's run this helper function. And let's input our k prediction here, 4. There we go, we got it, great job. Now let's keep going to prediction strength. Let's open it up. And the first thing we're going to do is run this function here. So this is a helper function that's going to help us calculate the prediction strength. Now, if you want to try and implement this by hand, by all means, be my guest. Now, just a refresher, prediction strength is a measure of cluster stability or how well the clusters generalize to new data. So let's run this helper function. Now it says split the data into a training and testing set similar to a supervised algorithm. So in this case, we're going to use the train test split function available from sklearn. All right, let's run this. Now let's set the range of clusters between 2 and 7. So it's going to be the same as what we did before. We're going to go end clusters. Now again, we're just going to go a little bit further from 2 to 11, not 2 to 7, just so we can see a broader spectrum. Let's run this. And also, let's put in a blank list so we can store our prediction strength so we can plot clusters versus prediction strength. Let's run this. Now, for each k, fit the model, get cluster assignment, and prediction strength. So we're going to do similar to the elbow plot where we're going to have a for loop, but there's going to be a couple more steps. So the first thing we're going to do is go into our for loop. Now we're going to fit the model on the training set. Now let's fit the model. Now the next thing we're going to do is get the cluster assignment for the train and test set. So in this, or another way to put this, is we're going to get the labels from the predictions from the training and the testing sets. Now we're going to get the prediction strength. So remember, we have a helper function. What the helper function returns is a list of prediction strengths, the minimum prediction strength for each cluster for that k. And it's going to return a list. So we're going to store that list in a variable called pred strengths. Now we're going to call our function. And we're going to pass in the X-test subset, the test labels, and the cluster. And finally, we're going to append the minimum strength of this list of prediction strengths for this k to our list called prediction strength. So we're going to have one prediction strength for each k. Let's take a look at our prediction strengths. And we see we have a list of prediction strengths that correspond to each K. We have starting at 1, 1, 1, and then it dips down to 0.7, 0.7, 0.7. Now, if you remember, Burkov recommends taking the highest number of clusters that is above 0.8. So based on that recommendation, we would take 2, 3, and 4 because our range starts at 2. So this is 2, 3, and then 4. Let's make a plot to visualize the prediction strength versus K. All right, so we take a look. On the x-axis, we have our estimated Ks, and on the y-axis, we have our prediction strength metrics. We can see at 2, it's still high, 3, it's high, 4, it's high, and then it goes down to 5, and it dips below this 0.8 threshold. So by this rationale, 4 would be our estimated number of clusters. Let's put that in. And that is correct. Now again, let me know what you think about this video and exercises such as this, comparing and contrasting two different methods. If you duplicate the 100-page machine learning Notion page from our Notion, please let me know how it is, if it was helpful, if it was not helpful, if something was confusing and what was clear. And if you liked what you saw, please comment, like, and subscribe. It really helps us out. And we'll see you in the next video.